So, if you're like most students, you took this angle challenge and were probably really confused by it. And that's okay. It's okay to give it a shot, see what you know, see what you don't know, so that this video hopefully can, if you pay attention, will help you understand some very important ideas in our GeoGebra or geometry, and understand that geometry is just basically knowing relationships and some angle pairs and things that we've been learning through this unit. We're going to apply in these challenge questions. So I'm going to explain how to get all these angle variables and their measures, their values. And at the end of this quest, you're going to try another challenge and see if you can find a lot more than you did before you watch this video. So let's get started here. Some things that we need to know for this challenge. Okay, so what we need to use to solve this angle challenge, let's take a look at here. We got some angle, this is kind of a summary of some angle pair relationships that we've been going through in this quest. So now let's try to make some sense of it. If you don't have notes on these angle pair relationships and some other bigger concepts like isosceles triangles here that I'm going to talk about, please get the notes down. This is important, and again, we're moving into logic, and this is a big piece that gets us to understanding some proof and a process of thinking, basically. Okay, let's talk about some of these things here. So, one thing that we need to know for this challenge is that in an isosceles triangle, the base angles are always congruent to each other. Okay, so for example, I'll use green here. Here's an isosceles triangle, right? So if I denote it by showing that these two sides are congruent to each other, then we know that this is a triangle. Two legs are equal to each other. And remember, the sides that are equal are what we call legs. So this is a leg, this is a leg, this is the base. And base doesn't just mean on the bottom of it. The base is just really the side of the triangle. I'm going to group these together here. So it's just the side of the triangle that's not congruent. So if you looked at a triangle that got, say, rotated, then the base is still this side. It doesn't mean the bottom side. So please understand that. But it's nice to see isosceles triangles like this because, again, our eye, we like horizontal. Okay? So anyways, the base is the side that's not equal to each other. Therefore, the base angles would be these two angles down here because they are formed by the base and the leg. So they're called base angles. This angle, by the way, up here, this is what's called the vertex angle. So take these notes down. These terms are new, at least to me. You may have heard of these before. I hope you have in middle school. But this angle right here is called the vertex angle. So I put this picture up here to help us understand why this is called the vertex angle. This is just a regular polygon. I hope when you look at this you identify that as regular. And you can see our rotation method, right? If we're going to take D and rotate it to C, C to this point H, and so forth all the way around, or just follow that circular path, right? It's the rotation concept, so we had to rotate this angle, and this angle, and this angle, and this angle. All these angles are the same. So we know that, oh, if this is a hexagon, 6 sides, right, 6 angles, we know that we could take the 360, divide it by 6, because there's 6 angles. Each of those angles is 60 degrees. So these are what we call the rotation angle, also known as the vertex angle. Okay, because this is the vertex of all these rotation angles that we used, right? So, and also, another key thing here, since all these radii of the polygon, or of the circle, since I have a circle here as well, are congruent to each other, right? So I'll put the little congruent marks. Then aren't each of these little triangles not only equal to each other, or congruent to each other, because they have the same sides and angles and all that, but they're also isosceles, because in each triangle, these two legs, or radii, whichever context we want to talk, are the same length. Therefore, these are all little isosceles triangles. Okay, so that's why these angles here, when you look at a general isosceles triangle in geometry, this is a vertex angle. Okay, so sorry I had to talk a little terminology here that we haven't gotten before, but I figured this was the time to do it. So take notes, make sure you understand base angles, vertex angle, legs, and base of an isosceles triangle. Okay, so anyways, we need to know that the base angles in an isosceles triangle are congruent to each other, and it has to do with that symmetry concept, right? If you draw that perpendicular bisector, then we have two triangles, the left and the right, that are reflections of each other. Therefore, this angle right here, when it we reflect over this line, would just map onto this angle here. So they have to be the same, right? Reflections are our argument for that. Okay. Vertical angles are congruent. Remember, when lines are cross each other or intersect, there's always going to be two pairs of vertical angles that are formed. So this angle would be congruent to this angle. Vertex angles are the angles across from each other. Okay, and then this angle here and this angle here would be congruent to each other, right? And you may put a little line through there, or you could double up the lines to show congruent. Okay, either way, they're just congruent marks showing congruent angles. Okay, so we know vertex angles are congruent to each other. Linear pairs are supplementary, meaning they equal their sum if you add up the two, hence the word pair. Add up to 180 degrees, right? So this angle here, if you add it to the measure of this angle here, they have to equal 180 degrees because they make a straight line, right? So we have to remember linear pairs are supplementary to each other. And we need to be able to take a number and find its supplement, meaning the other angle that adds up to 180, quickly. So use a calculator, use your head, use whatever you need to be able to find that answer quickly. But understand that concept. Also, with this triangle here, I put this in blue. Angle sum of a polygon, remember, we could use a formula to find it, or we just need to know the angle sum. Like in a triangle, if you add up all the angles, hence the angle sum of a triangle, that's going to equal 180 degrees, right? In a hexagon, there are 6 sides. So if you don't remember the angle sum of a hexagon, we can use our formula that we got, and remember it's the number of sides. So in a hexagon, the number of sides would be 6. 6 minus 2 is 4. Remember, the triangle method from one vertex, we would make 4 triangles. That's what this little thing in our rule means. You always take the side number minus 2, number of triangles we can make. And since each triangle sum is 180 degrees, then we take that times 180, 4 times 180. 4 times 100 is 400, right? And 4 times 80 is 360. So if you add those up, 700, oh my bad, 320 degrees, not 60. So if we added those up, we'd get 720 degrees. So that would be the angle sum of a hexagon, right? Just another example of using our angle sum of a polygon rule. But no, in a triangle, the angle sum is 180 degrees. In a quadrilateral, 4 sides, use the rule to prove this if you need to, but their sum, remember, is 360 degrees as well. Okay? So those are 2 of our main ones that we need to know. Just, it's mental math. Try to be quick about it. Store these somewhere in your brain to remember. Triangle, the 3 angles add up to 180. In a quadrilateral, they go up another 180 degrees, so 360, because we could add another triangle to. Anyways, and then the last one here, parallel lines and their special angle pairs, right? Remember that corresponding angles, say like this angle and this angle, or this angle and this angle, for example, or the other 2 pairs I could illustrate, are always going to be congruent. Know the alternate interior angles, so this angle here and this angle here are congruent, right? And think about this, 1 and 3 are vertical, aren't they? So we know their angles are the same. So that makes sense. If this angle has the same measure as this, and this has the same measure as this, 5 and 1 are corresponding. They have to have the same measure. So we can start putting some thought process and explaining why these have to be true. Okay? And that's part of this challenge. Same side interior angles are always supplementary to each other, right? So supplementary. This angle here and its same side or consecutive interior, however you want to say it, they have to add up to 180 degrees. A quick argument for that would be this. Look at angle 3 and angle 2. We have a line. we have they're two angles, right? And since the measure of 3 and the measure of 2, they're a linear pair, they have to add up to 180. 6 and 2 are corresponding angles, so they have to have the same measure as well. So if 6 and 2 have the same measure, 3 and 2 add up to 180 because they're a linear pair. Then wouldn't 6 and 3 also add up to 180 because, again, 6 and 2 are the same? So that's a quick argument of why same-side interior angles always add up to 180 degrees. So use that fact. Okay? So please, guys, go through, make sure you have these notes written down. This is very important. This is summarizing a lot of angle concepts. So please make sure you have these notes, okay? The next video is going to go through using these properties and solving that angle challenge.